So our next speaker from Intel, so Rosen Xu, is going to present you one feature that is, in my opinion, one of the best candidates to be offloaded in hardware, which is quality of service. So that should just work. So let's see.
Okay, thank you. Hello. Okay. 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 The timer. Okay. Hello. Can you hear me? Hi. Okay. That's okay. Let's start now. Time start. Okay. Oh, okay. Hello. Hello. I'm Rosen. I'm from Intel. Okay, and with hundreds of VMs or thousands of lightweight containers running in the same physical machine. Okay. Today's multi-tenant cloud networking rely heavily on the visualization. So this results in tens of thousands of traffic classes and flows per end host. So fine-grained HQoS is very important to cloud networking. And this is my topic of today. Okay, it is DPDK-accelerated partial offload for fine-grained HQoS. Let's start now. Okay, and this is the agenda. Firstly, I will present a generic HQoS use case. Okay. Then I will list the existing DPDK HQoS capability. And then I will list some hardware limitation for fine-grained HQoS. And I will also list some FPGA-based acceleration and the partial offload of HQoS. Okay. Let's start now. There are three key decisions in HQoS processing. Okay, the first one is which flow a packet belongs to, and the second one is when a packet becomes eligible for scheduling. The last one is what order to schedule packet flows. And this diagram shows a generic HQoS model in this presentation. Okay, and you can see all the packets ready to be scheduled, for transmission, are classified and in queue. Okay, are classified and stored in queue. Okay, for the and before they are in queue. Okay, the packet will to take metering. Okay, in the metering, and the packet should be marked in one color of red, green, or yellow. Yeah, and after metering, the congestion management makes decision which packet should be passed or should be dropped. Okay, and this is the generic. Diagram. Okay, we can find for HQoS there are many components. Okay, they are classified, metering, congestion management, shaping, and scheduling. Yeah. And each component has its private algorithm. Yeah. Oh, sorry. And currently, DPDK has fully supported all the HQoS components. We can find that DPDK has provided metering functions. Okay, it can support a single write or two write. Three-color marker. Okay, it also can provide the blind mode or the color-aware mode. Okay, in the ITTM ops. Okay, DPDK has provided the constraint management and shaping. Okay, and it has supported all the HQoS components now. For the tens of thousands of flows in multi-tenant cloud networking. Okay, there are some limitations for the hardware. I think the first limitation is limited and no scalable hardware queue number. Okay, as we all know, the most hardware NIC queue number are about 1,000. Yeah, But for the multi-tenant cloud networking, okay, there are tens of thousands of flows, okay. So this is the gap of the queue number, okay. The next limitation is lack of flexible for packet scheduler, okay. Being implemented by the silicon design, okay, it is fixed. It is fixed schedule algorithm, okay. So it is less flexible. And the last limitation is the border memory, okay. The result of sharper and the scheduling depends on the memory. It can keep the packet, okay, especially in the hierarchy and the congestion scenario, okay. So that means more memory it keep more packet can result well for the sharper and the scheduling. So that's the limitation of the hardware implementation. Okay, we can find there are different telnet provide different flows. Okay, after classifying, some of flows will map into one hardware queue. Okay, in this hardware queue, it cannot identify which flow it belongs to. Okay, so that's the limitation of current hardware NIC implementation. Yeah. And in the next slide, I will present our work on the patch offload. Okay, this patch offload is a cooperation between the FPGA RTL design of HQoS and the DPDK. Yeah? And our reference IP is based Intel Park N3K card. Yeah? And this is the programmable acceleration card. There is Area 10 FPGA. It is the biggest Area 10 in this card, and it also include two XL 710 chips. Okay, for the packet process. Yeah. In the FPGA IP, okay, we have implemented most of component of the HQoS. Okay. We have provided congestion management. We also provide shaping and scheduling. Okay, for the there are many different algorithms for congestion management. Okay, we can find tail drop, ride, or double ride. Okay, but the most efficiency, the most efficiency wise is double ride. Okay, and there are also many different private algorithms for the double ride. Okay, and this is our reason now. Okay. We can find that our traffic class has 7 states. Okay, it's S0 to S6. Yeah, and each state and each traffic classes has a different threshold for in-queue and DQ. Okay, so if we go this path, okay, from S0 to S1, okay, the double ride will calculate the average queue length when packet is in queue and DQ. Okay, it go to different states by the threshold and this FSM. Okay, yeah. In the left side, it is the packet drop waterline for in queue and DQ. The upstairs is the in queue waterline. Okay, we can find, and then the downstairs is the DQ. Before the, as I has described before the construction, we needed to take metering and mark for each packet. Okay, so every packet will take one color of yellow, green, and red. Yeah, and for the red packet, all the packets should be dropped. Okay, because that means the traffic is in construction. Yeah. But for the yellow and the green packet, we have different water lines for these two packets. Okay, in the in-queue, we can find if the yellow packet, if the yellow packet include the traffic class and the traffic class in the S0. Okay, all the packet can be passed. Yeah. If the traffic class in S1 and S2, the yellow packet may be random dropped. Yeah, and in other state, okay, all the yellow packet may be dropped. So this is for the yellow packet in the in-queue. Okay. For the green packet, okay, we can find if this traffic class is in the state of S0 to S3, okay, all the green packet will be passed. If the traffic class in S4 and S5, okay, the green packet may be random dropped in this traffic class. Okay, in the S6 state, okay, all the green packet may be dropped. Okay, and this diagram is for the in-queue. Okay, and the downstairs for the DQ. DQ is different than in-queue. Okay, for the right packet, okay, we can find in S3, in the S3, it is dropped. It is passed for all the yellow packet, and the S1 and S2, okay, it also random drop for the yellow packet. In other state, in other state, okay, all the yellow packet may be dropped. Okay, it is the same as the for the green packet. It is the same as the in-queue. Okay, but the threshold for the in-queue and the DQ are different. So the packet drop or not, it depends on its color and the current queue status. Okay, so that's the algorithm for the double write. Okay. And besides the congestion management, we also provide the shaper and the scheduling. Okay, currently we provide a 3-level hierarchy shaper and the scheduler. Okay, for the user point of view, we provide 16.4 kilo flows. Yeah, so that means it can provide 16.4 kilo flow to be used by the users. Yeah, and each 8 flows were mapping to one flow of VT line. Yeah, so in the VT line we provide 8 kilo flows. Yeah, and each flow of these 8 flows can be mapping to one port of these 8 ports. Yeah, and for the scheduling, we and each scheduling node will have two scheduler. Okay, the first is the DWR, and the second is SP, and the priority of SP is higher than the DWR. SP, that means strict priority. It is the highest. It has the highest priority in this scheduler. Okay, in each scheduler output, we provide a shaper. Okay, so you can see we can provide a shaper for each scheduler. Okay, yeah. And besides the scheduler, we also provide some statics. Okay, for the ports and the byte counters. Yeah. And this is the shaper and the scheduler. Currently, we have upstream our code for this RTRP. Okay, we have upstream in DPDK 1905, and the users can get this software and can get an API image. Okay, from Intel, can try this API. Yeah, and we have provided all the implementation for the write and for the hierarchy shaping and the scheduling. Okay, and after we have cooperated with RTL team for the API-based hierarchy QoS, okay, we get some summary. Okay, some is good, and another is it is not well. Okay, the firstly we found it is for the API design. Okay, it is more configurable and flexible than NIC. Okay, it can provide tens of thousands of flows, and it is very flexible, provides different scheduling algorithms by update the API bitstream. Right? And it also provides fine-grained hierarchy QoS for multi-tenant cloud network. Okay, you not only meet the requirements of cloud, it also can meet the requirements of NFV. Yeah, and we also found some limitation of this API design. Okay. As I has explained in the last slide, okay, the result of scale and the shaping depend on the local memory, but currently there are to buffer this packet in the card. Okay, the packet N3K card needs a lot of memory to to packet all these, to buffer all these packets. Okay, it will take a lot of memory. Yeah, and it will make it, and it will make the development more complexible in RTL design. Yeah. So our proposal is can software take up some parts of HQoS, because in CPU side, okay, we can find there are much more memory, okay, in the CPU side. So can we reuse the CPU side memory or for the packet buffer and for some other parts of HQoS? Yeah. And currently we are doing this work now. Okay, in this work we divide our workload in the different parts. Okay, some part is in the API side, another part is in the software side. Okay, as I have introduced in my last slide. Okay, the HQoS have several components. Okay, some is classify, we can find, and this is the congestion management, and we can also find the scheduling and the shipping. Okay, so our work is that software will take the packet classify. Okay, you can find. We will enable some thread for packet receive. Okay, and in the packet receive, we take some packet pass. Okay, and after passing the packet, okay, it send it to the classify thread. Okay, in this classify thread, we will take packet classify and identify the packet belongs to which flow, and it will to dispatch different in-queue thread, okay, by the load balance module. Right? In the in-queue thread, okay, we will tag the metering, okay, to decide what color this packet belongs to. Yeah? We also will enable double write to drop a packet or to take the next stage. Okay. And in the TX thread, okay, we will merge this packet, okay, and send the queue info to the FPGA. Yeah. And in the FPGA, it will get the queue info, but the packet is buffered in the CPU side. Yeah. So the FPGA will get the flow information. It will get the flow information, and it will schedule and shape by the flow information, and after the scheduling, okay, it will generate the credit. And this credit will send to Nick, and Nick will get the packet from software. Okay, and this is our work for the partial offload HQoS. And this is the cooperate between FPGA and the software. Okay, and it can benefit software and FPGA. Yeah. So, any questions? Hello? Any question?
So I'm not sure I understood the last slide. So you were saying that everything can be done in the FPGA, but here you're saying everything will be done by software?
Yeah. In the software, okay, okay. There are many components for the HQoS. Yeah, we can find that there are classify, congestion management, and shape and scheduling. Okay, we only assign the shape and the scheduling in FPGA. Yeah, but the packet is buffered in the software. In CPU side memory. Okay, and some information. The software will generate some flow information. Okay, it is not a DMIQ. It is flow information. It will send it to the FPGA. Yeah.
So this is egress shaping.
Yeah, it is ingress.
Egress.
Egress, yeah, egress. And the shaping is used more widely in egress. Yeah. For ingress, it is metering. It's more used. Yeah.
So packet all comes up into the LLC. Most of the work done in DPDK. On the way out, you do, because you've got way more queues in the FPGA, you do egress shaping on the way out.
So any NIC that can support a lot of queues can help with the shaping.
We have implemented a reference design in packet and 3 car. Yeah. Okay.
No, you can take any NIC on the way in, on the way out. You have to DQ on these on the Excel 710s?
Okay, we can discuss it offline. Yeah. So any questions? Please.
Do you support ECN?
The placing of the metering. Yeah.
No, it's more about marking packets that hit a certain threshold before you start dropping.
No. The ECN implementation is in the software, so we can take different places for the software. So it is more flexible than the hardware based. Yeah. So it is the cooperation between software and FPGA. So, okay. And any other question? Okay. 10 minutes free. Thank you.